Okay, so we are live. Hello, everyone. Hello, Kenny. Welcome to the Fab Academy Recitations. Today is a special day because we have one of the very pioneers of the Fab Lab network, Kenny Cheung, who is now a doctor that actually, or PhD, that came out of the Center for Bits and Atoms at MIT. But he also has been setting up Fab Labs, shotbots, doing crazy projects all over the world, including with us in Barcelona. And also doing crazy things like going through the US in a mobile Fab Lab. Back in 2007, I was part of that as well. And now working in NASA, finding out how we're going to inhabit space and how we can make almost anything out there in the space, probably. So, Kenny, thank you very much for joining us. With you, following you will be around, I guess, 400 people in more than 75 Fab Labs in the world. So you're talking to the network, and actually you have been part of building this amazing international community. Thank you for joining.
Nice. Hello, everyone. I'm happy to be joining you. The talk I'm going to give and the slides I'm going to give have to do with some of my recent here at NASA. But I want to leave as much time as possible for the question and answer period, and feel free to ask questions that are more specific to the Fab Lab work that I've done, or that more directly relate to those. And I'm happy to answer any kinds of questions that you have. So I want to start a little bit about the research. And so hopefully you all see just the white screen right now. So there's this notion that in all things, there's this sort of body of work that's the stuff that we know. And so in this blob, there's the things we know how to do, the things we know how to make, and the work that you do a lot of times day to day, or the things that you do even in the kitchen or any sort of creative task, oftentimes more or less falls within this blob. And what you try to do as a designer or as a scientist sometimes is to sort of expand the size of that blob, of the things you know how to do, or even the things that everybody knows how to do. And you sort of incrementally expand the size of that blob, and you eventually get to a bigger blob where we know how to do a lot more. That just sort of keeps growing, the body of knowledge of the things we know how to do. And there's a sort of strategy of research that says that you could either try to work within the blob to sort of fill in holes. You could purposely get as close to the edge as you possibly can. Or you could pick a point all the way out here and aim for there. And in doing so, you know that your odds of getting there are fairly low. But even if you get part of the way there, you have a much greater chance of making some progress. And that's truly outside of the body of work that we already have. And in very exceptional cases, you could make a sort of jump and completely change the landscape with a completely new sort of way of thinking about things. Now that, for instance, in science is extremely rare, but it does happen, where you have things like calculus or general relativity. And so this is sort of as a conceptual framework for how far out you might look, and that it's pretty, it's not only legitimate in a way, but really important for some of research to look extremely far out. Now, I happen to be fortunate enough to work at one of the places that takes that diagram and treats it as sort of a physical diagram. And so that little blob out in the corner is actually essentially out in the cosmos. And this notion of a completely new blob sort of starting up for us is literally the notion of a complete self-sustaining civilization for human beings that's separate from the Earth entirely. And so the consequence of that kind of that research, that exploration, you get the kinds of results like a lot of the core inventions that have come out of space research that just come down to everyday life things. And so there's thousands of things in everyday life that have come directly from trying to solve the problems of space exploration. And so these are just some of them. Some of them are sort of misunderstood. There are some things that are attributed, like Velcro and powdered orange drink, that weren't invented by or invented for space exploration. However, they might be used in space exploration. But things like GPS, core search and rescue systems, core technology to infant baby formula, scratch-resistant coatings for plastic lenses and UV reflective coatings for plastic lenses. Some of the structural dynamics software that's used for almost any kind of structure, especially that has to do with wind and motion dynamics. A lot of core water purification technologies, any digital image sensor, viscoelastic foam, the tensile fabrics that are used in architecture were invented for spacesuits. Mass flow sensing and pumping equipment used in artificial hearts. Firefighting clothing, and one of my favorites, most people don't realize that core cloud computing technology actually started off as technology for computing clouds. And so this is the kind of sort of fan out in applications that you get simply from picking a point so far out, the scope of the problems is really immense. And so this is the facility that I work at. The body of water in the background is the San Francisco Bay. And it's Ames Research Center in its own little enclave called Moffett Field in California. This picture was taken a little while ago, but it's mostly correct. Off to the side of the screen is the Google campus. That gives you an idea of exactly where we are on the peninsula. And so the large building that you see in the foreground is the world's largest wind tunnel. And we have several other smaller ones and faster ones on the campus. And so the kinds of facilities that we have include a computing system that can do things like the simulation you see in the lower left, where 1 pixel on this screen equals a kilometer by kilometer patch of the ocean. And this system can take satellite data and estimate the motion of the water in that 1 kilometer by 1 kilometer patch for the entire world, and simulate the expected motion of the water for every 1 kilometer in depth. And so you can scan down all the way to the ocean floor. And these kinds of simulations are critical to climate models. And then in the upper left is the largest vertical motion simulator that gets used to train astronauts to land flight vehicles and to fly space vehicles. And this was the system used to train astronauts to fly the space shuttle, which was a kind of plane that only gave you 1 shot at landing. So it was pretty key that they trained on a system that was as realistic as possible. In the upper right is one of our wind tunnels. And in this case, it has a large launch vehicle. This is a model of our Space Launch System rocket, a heavy lift rocket that has the capability of sending things to Mars. And in the lower right is micrometeoroid test impact. So these are the test that you see is testing shield materials for spacecraft. And the speeds of these tests are on the order of tens of thousands of miles per hour. And so the kinds of things that we look towards, this sort of point that's further out, one of them is like I mentioned, a standalone space civilization. And so the question there is, what does it actually take to sustain human beings without the Earth? And one of the things we learned from this, of course, is how precious the Earth is. But in the engineering, in the process of trying to engineer these kinds of systems, we get that much closer to the systems that we need to explore other planets. And in developing the technology, we end up developing things that are very useful for sustainable technology on Earth. And so in this case, these are two very particular architectures. These ones are typically referred to as O'Neill cylinders and world ships, where the idea here is you get artificial gravity from these cylinders rotating. And there's been several designs for these at various scales. These pictures show pretty much the largest scale that has been proposed. And this design is called a Bernal sphere, where again you see everything attached to the outside. The sphere is designed to rotate for artificial gravity. Now, in my lab, we try to focus all the way across the spectrum, much like in any Fab Lab. And we do have a user facility, a community facility that we call the Space Shop, which operates as a Fab Lab. And we're working on expanding that to outside of the fence in the center so that it is publicly accessible. But so far, we try to bring in students as much as possible. And this is Holly. And you see there a teacup teapot that she's designed in antimony. And she's 14 and came to us through one of the local science fairs. And she's been working on some really nice projects in order to learn how to code, and for her science fair work, where her sort of first big coding project has been topological optimization for digital materials. And so for the digital materials, the structures that we're working on include things at this sort of size. And you see there, that's Christine working on assembling the structures, and the white pieces are some small robots that we're working on that can live in these structures. And hopefully we can get them to do the kind of work that Christine is doing manually there. And this is Ben, Daniel, and Sean, and some impromptu testing of some of these structures. And so the testing is really quite important. And a lot of the testing actually still comes down to pretty first principles stuff. This is Amanda, for those of you who haven't met her already. And this sort of challenge of testing things. This is a video that should play.
You're on. And you laugh at me.
So this always starts, you have to start somewhere. And so that was me. And somehow from that, they've let me into work at NASA. And so along the way, if I can get this slide to advance. So along the way, you keep trying and you keep learning and you keep developing the model for the bubble that already exists. And the only way that you can work at the edge of that bubble of stuff that already exists is to understand the bubble that already exists. And so to do this kind of work, it's really important to realize where you are and where that bubble of stuff that we know, where that is relative to you are at that time, where you are at that time, and then you can position yourself on the edge of the bubble and really look out farther. And so this is one of the early wings, digital wings that we put together at MIT, and this is some work that I put up from that. And so this is an interesting wind tunnel that's actually a sphere, and the test section is suspended inside it. So what you see here is the test model in front of the turbine that pulls the air through the wind tunnel. And this whole section is suspended inside a sphere so it can rotate. And the idea there is it can point up a little bit, which makes it so that you can actually fly something inside it. And this is a slightly more recent model showing that what we're trying to do with these is show completely new ways of controlling the wings. So if you fly on an airplane, you look out the window and you see these discrete patches, these hard rectangles that move in and out and up and down. And what we're showing is that with the system, we can make the wing simply bend to different shapes and even flap, and have as much control over the airplane as you would with the traditional ailerons and flaps, but with quite a lot less drag and with an extremely lightweight structure. And both of those things save a lot of energy in flight. And so expanding the whole project behind that wing structure and connecting that back to the space systems has to do with core to that is the fact that they're made out of these digital materials. So the discrete units. There's very few different types of them, and it's well suited to robotic assembly. And so this provides a different landscape for the approach in this cartoon, where you see this sort of a relatively large catalog of units that compose these robots, and each unit only has a couple places, or in most cases just one places where it goes. What we're proposing is that we can create things that are just as functional and have as many or even more uses out of a very small library of components. We do use a lot of the components, but we can do essentially the same thing. So then we have a strategy for building almost any structure we need, and in a way that allows us to repair them very easily, or even redesign them after they've been built, and reconfigure them. And so we're starting to work on these structures, and even making them, we're starting to work towards composing those structures out of units or building blocks that themselves can speak to each other, transfer power to each other, and so we're looking at the entire structure being active in a way, everything, all of the structure being able to sort of report to its neighbors and back to us, really, as to how it's doing, which is a concept called structural health monitoring. And we're interested in seeing what kinds of capabilities we can get out of taking the structural health monitoring and distributing the problem and integrating it completely throughout the structure. And this is the rocket that that this experiment flew on. So we have put some things in space already. And so that's just sort of this tiny step towards answering this question of how do we even start to go about building these kinds of systems, knowing what we know now about how to actually make something and how to actually make something in space. We're very far from being able to make something this size as a single unit. And one thing we do know from cities and from urbanists is that building these kinds of things, something this scale, as a single static design, top down, as if you could build the entire thing in a factory, is not something that seems likely to work. And we actually seem very limited in the size of a factory that is, and the complexity of a thing that can be made in that way, where you conceive of and engineer and design the entire thing and then expect it to be not just functional in all its levels of complexity, but to even work, to even be able to finish it. We seem to be limited in our current methods to things that are much, much smaller than these concepts of space civilizations and world ships. And so I want to close the talk and open up to questions with this, I guess, another sort of belaboring of this notion of how far you look and where that gets you. And so the photo on the left is actually just, at this point, a small number of all of the planets that our Kepler spacecraft has found. And so on this question of whether or not there are habitable planets out there already, what we used and what we still use, one of the things in terms of the body of knowledge that we have, that we use to think about this is just when you look up at the night sky, you see all of these stars. And you can ask the question, how many of those stars are like our star, the sun? And how many of them have a planet that's like the Earth? And so this now is already confined the question to places that are like ours. So this is already a smaller question than whether or not there's life out there. It's now whether or not there's life as we know it out there. And it wasn't that long ago, really just decades ago, that we thought that there were relatively few planets out there in general that were a distance from their star, that given the temperature of the star, that planet could have liquid water on it. And now we know that there are actually quite a lot, a large proportion of the planets that are out there, a much larger proportion than we previously thought, are in this habitable zone. And not only that, but a much larger proportion of the stars out there actually do have planets, which is a very exciting new piece of our knowledge about not just our solar system, but the cosmos. And so this idea of being able to go to other planets, or there being other planets sort of worth going to, or bringing life as we know it to, becomes more tractable. And so this was just in 1869. Everett Hale published this article called the Brick Moon, and this was completely out there at the time. And the idea here was basically to put somebody to put people in orbit, and to put up a satellite as an artificial moon. At the time, we didn't even have engineered flight, much less a good understanding of what it would take to put something into orbit. And so at the time, this was essentially entirely fiction. This was completely out there. But it only took us 100 years to get to the point where this notion of a satellite or a brick moon is sort of pedestrian. We can do that relatively easily now, and even make businesses out of doing that. And so we look farther, and to see what we can think about if we think about what the next century's brick moon might be. And so with that, I'll open it up to questions.
Thank you very much, Kenny. This is really exciting, but at the same time, somehow opens the question. And I want to throw this first one on: is our planet really that bad that we actually need to go somewhere else? or some people might claim we haven't really made one work, and we're already looking for more. Hi. So the question is, it's more like philosophical. Where should we put our energy first? Fixing this one or finding some more?
It's a good question. It's a very good question. There's an extent to which putting some energy towards finding a new planet for us, or create the world ship. There's an extent to which we sort of already know that doing that work goes towards the kinds of discoveries and so, for instance, photovoltaics were developed for space applications. As a concept, they didn't make sense when they were first discovered, and they certainly didn't for Earth applications. They were immediately taken up and developed, and an industry was built around them because they do make sense for space applications. And so when you consider even just the satellite problem, you're in this extremely small, confined, closed system, and all of the engineering that you have to do for that, with the one caveat that you spend so much energy getting up into orbit. But once you're there, you basically just have the sun. You have this microcosm of the problem of an engineered system on Earth that is a sustainable engineered system. And so, to some extent, we're trying to address the materials problem. The fact that we've been able to address the energy problem of that has really developed the battery systems and the photovoltaic systems and low power, in particular, extremely low power electronics that really enable many of the sustainable, what are seen as sustainable engineered systems for Earth applications. And a lot of what many would consider to be the most important applications for all of the equipment that we're putting up there. And that's a huge part of all of the space agencies, not just NASA. These planetary studies, and the easiest to study planet and the most studied planet in all of these planetary studies is the Earth.
So, Kenny?
Yeah?
I have let's see, I'm getting some dropouts from you. Can you hear me okay?
Yeah, I can hear you fine.
Okay. I have a three-part trajectory question.
Okay.
When we met, you were an architecture student. How did you go from architecture to space? The first part.
Okay.
The second part is, as a grad student, you did 10 things that could be a thesis. How did all those projects, out of all those projects, how does projects become a thesis? And then when you finished your thesis, you had lots of options. You made a somewhat unusual choice to become a civil servant. And so talk about architecture to thesis to civil servant.
Okay. So I still do think of myself as an architecture student. So the way I see that hasn't changed. I think since then, I've learned how to become other kinds of students as well. So if anything, that's the only thing that's changed. And so the progression from there to to where I am now, I guess you could say in some ways was driven by the 10 different projects. Turning one into a thesis, it's a good question of how to pick. I mean, at some point you just sort of see that the scope of what you're working on is so broad that you sort of dial in, and you couldn't let it go if you tried. But sort of like not letting go of being any particular kind of student. I wouldn't say that I've let go of all of the other projects either. But you do change how you think about things. You can't work on too many things at one time. So some of the things you sort of table. You put it on the shelf. And you're sort of, it surprises me how often something comes back to be important in ways that you wouldn't expect, in terms of the way you thought about a project, that maybe at the time you put it on the shelf you think you hadn't finished. But something about what you did there becomes important to how you think about something new. And my choice to become a civil servant, I feel very lucky to have that choice, to feel like, to have felt like I had that choice, and to have had, I guess, all of the other options. And I owe that somewhat to having the opportunity to work with all of the people that I've had gotten to work with in the Fab Labs, because that gives such a broad perspective as to how people work and live, and what motivates them, and the fact that the more directly you can take a role that is about that it's about working for people in the end, the more satisfying it can be.
So yeah, I think you're a really interesting example case for the Fab Academy students in two sides. On the one side, I think really just you're a designer, and it doesn't make sense to append a different word to it. You design stuff. But on the other hand, you do domain homework. You don't just rely on the designer, but you learn a lot about domains to be able to practice it. And there's this balance of not just being a designer, but also doing deep domain-specific homework and not being a dilettante, that I think is a good motto.
Thank you.
Good. So with that, I'll listen in and let me open it up to questions.
Yeah, we have 4 questions. I'm going to start for the first one. Francisco from Sitges. He's asking, what's the structural dynamics of what you talked about at the beginning?
Sorry, what's the structural dynamics of the work that I talked about?
No, structural dynamics software.
Oh, Oh, it's called Nast. So in the work that I'm using, or the one that I mentioned that's used in more generally?
It was mentioned, spin-off assets in space development.
Yeah. So Nastran, Nastran, and it's one of the leading reasons why Fortran is still used.
Okay.
But it's an incredibly powerful piece of software that still gets a lot of active support. And the most recent use of it that I've heard is for large-scale, megawatt-scale floating wind turbines. I mean, this software gets used for everything. It gets. I think I might have shown a picture of a roller coaster to remind me about that software.
Okay, thanks. Victoria Bell from Detroit. She's asking if the flexibility of the morphing wings allow the plane to fly faster with less turbulence. I guess she's just talking. Yeah, go ahead.
That's a great question. Wait, is there more to that question?
No, that's it. I was trying if you needed to clarify, but is
that? We think so, yes. We certainly do think that for a very large plane, at the scale of what you would fly in, that you would be able to fly in a way where the passengers would feel a lot less turbulence. And part of how you would deal with that would create a lot less drag, and so you would fly for your flight. And if you could really manage the turbulence in some of the ways that we think you can, then you would in general be able to fly faster through a given amount of turbulence. So yes.
Okay.
So.
It's a good yes. So there is another question about inhabiting other planets, and if this is from Nisha Johnson. It says, I'm curious to know whether there is some fabrication that could be done in Mars to create a surface gravity same as that of Earth. Also, continuing with the question, saying pseudo-gravity being a solution while setting up colonies like the International Space Station. What about setting up colonies in planets? How they're going to be fabricated?
That's a
big one.
Two very nice questions. So the gravity on Mars is a fraction of what it is on Earth, but it's a pretty good fraction. To create more on Mars, the sort of ways that we know how to do that now would be to create a lot more mass. But there's the or not want more gravity on Mars. So you could create a habitat on Mars a centrifugal habitat that augmented the gravity on Mars, or what you would feel and interpret as gravity. But there are some reasons why that will get to my answer to the second part of the question. There are some reasons why the lower gravity on Mars could be a good thing. And so the second part of the question is, why do a space habitat versus orbiting another planet? Actually, there was another part of that question too. I don't forget. But that question is a question of resources. And the answer to that question is debated among the space civilization scientists, because we're not completely sure how easy it is to get at space resources that are on planets versus just out there in the form of comets and asteroids. It's possible that as we develop the technology, we'll find that getting the resources is a lot easier. And a large part of the reason why it's so much easier is it's not stuck in a massive gravity well. And so one of the biggest problems with going to another planet is the gravity well, and you're sort of confined to the set of resources that you have on that planet. So if it's not broad enough for what you want, you're sort of stuck. It'll take you a lot of energy to get out and get other resources, for instance. And so some people think that it seems that using asteroids for material needs, or even bringing materials up off of planets into space, better from a total energy standpoint, to create an engineered civilization for human beings than to do it on the planet. Now, in terms of the fabrication on a planet, or in general, assuming we're going to use the resources in space, whether it be on a planet or from asteroids and comets, to make things, to make these habitats, for instance, how we actually do that is a phenomenal question. It's a great question, and you know, we're trying to look at and one of the strategies is digital materials. One of the strategies that we are looking at is printing. We have one of our centennial challenges is 3D printing a habitat. And we have projects basically to create giant 3D printers that could operate, build these kinds of habitats.
Let me add a piece to that. A few weeks ago, I had to leave cut off discussion in the class, and it was going to. Here, let me share that. This event that was done with the White House Office of Science Technology Policy, NASA, the Mars team from NASA, and the person who had just stepped down as the chief technologist, the person who helped create DARPA's bio program, and the whole sort of cast and crew of The Martian. And it was exactly on this question about how we bootstrap the civilization. And so this is one of the science pushes of the White House. And one of the real interests of the NASA leadership about this idea, paraphrased, is how you leave Earth without luggage, how you bootstrap a civilization. And the really important research question is, what are the minimum building blocks to bootstrap a civilization? It's really the roadmap.
Actually, it's very funny because that's exactly the question that Francisco is saying.
One last thing, the videos were fabulous. God had all these amazing people, and they were so good. They're going to be part of the supplemental material in the home edition of The Martian. They'll also post it online. So those videos are coming. Go ahead. Sorry, Tomas, you muted.
Yeah, sorry. The question was, how or what would you pack for a Fab Lab for a space mission? Actually, is that you don't need to.
Yeah.
But there is another question about.
Oh no, sorry. Say that carefully. In that, I like to think of this as a engineering. You need to produce the building to make all the rest. But to bootstrap it, you need to bootstrap the RNA world. You need the building blocks that let you get up to the 20 building blocks to build it. So it's not that you need to pack anything, but it's very precise what you need to reduce the building blocks down to these 20 parts.
Yeah, there's a concept called the von Neumann probe, and it's interesting now to think about there being sort of different species of von Neumann probes, and the point of the probe is you can actually explore much faster if you send out a probe that the first thing it can do is find the resources with which to make a copy of itself. And so this will be familiar to the Fab Lab idea. And so this question of what is the Fab Lab von Neumann probe I think is an interesting one. I like that.
Okay, one more question from Very Moore. It's asking more about like the social, no? Social aspects of space. It's like what's the meaning of life in space, or what does federal governance look like in such a remote location? Or are these questions even important at this point? I mean, the effects on the physical body as well itself.
Sorry, could you repeat the questions again?
Yeah,
a little bit slower.
It says, are the people building this technology also thinking larger questions about human life in space? Like, what's the meaning of life in space? Or what does federal governance look like in such a remote location? Or are these questions even important at this point? I guess referring to the effects on the physical body.
So, Kenny, how would you architect a society, in other words?
Sorry, how would I?
How would you architect a society? You've described the physical part, but how do you back project the physical into the social organization?
So, one of the things that we've learned from the is that basically everybody who's come back from space has corroborated or explicitly conveyed the idea that the politics on Earth seem incredibly trivial when you get the perspective that you do of the smallness of Earth and relative to the cosmos. When you see all of Earth in a small part of your field of view, the whole perspective of what aspect of politics are important and what isn't changes vastly. And so I do think from the sort of completeness of the sort of effect of the space experience on astronauts, I think we would see something a bit different until we would get to something of Earth, right? It would have to be so big that you could start to ignore or not see the smallness of society relative to all of physics or nature, the whole environment around us, which isn't to say that we couldn't get there and then have the same problems. But for the time being, what we see in space is nations that are in a Cold War with each other, able to collaborate only in space. You've seen some interesting social effects to being out in space and having this perspective of the Earth. And the other thing is exploration as a goal. You know, in this case, it's physical. The easiest sort of way to look at it is it's physical exploration. But to be a civilization or to be a society where the primary goal is exploration, I think is kind of a nice thing. And in sort of small societies that are built on this, all the way down to the scale of the group that's on the International Space Station, which is a very small relative to not just what we'd like to do, but you know, the kinds of even just ships. I mean, as a ship, it's small. It's a lot smaller than ships that were used to explore the oceans, even. And so the kinds of societies that you build on these ships, when the goal is exploration and not necessarily conquering, is something different. And so I agree with what's implicit in the question that that it's very important to think about not just what the society would be in space, but what effect that would have on the society on Earth. And that's part of why working on space exploration is interesting to me.
Thank you. I don't know, Neil, do you have any closing remarks?
No, I think that's a nice thing to conclude on. And Kenny, you'll be at Fab 12, right?
Oh, we'll see.
Hopefully Kenny will be at Fab 12 so we can.
Yeah.
Okay.
But by the way, it's not settled, but I think what we're going to try to do at Fab 12 is have the big activity during Fab 12. The whole Fab Lab community makes a Fab Lab from Tartas to Recitations. And
I like that.
Okay. Well, thank you, Kenny. Thank you for joining us.
Thank
See
you.
you at least in Fab 12, if not before, hopefully. Thank you, everyone. Thank you.
bye-bye, Kenny.
Okay. Bye-bye.